Okay, so we spoke about the moment vector. So by looking at mz, right? So we know that the head of the moment vector is compression. The tail end is tensile, right? And you also look at the moment vector for my. The head end is in compression. The tail edge is in tensile. So if you are having problem visualizing this, what I will encourage you all to do, which will help us or help all of you a lot, is you just draw a vertical arrow, right? And you just use right hand rule, and how your hand grabs, right? It is grabbing in this way, right? So this is in compression, and this is in what? Tensile. Okay. So a lot of times students have problem visualizing which one is tension, compression. You just draw this arrow. Then what I tend to do is I will ask the student to rotate the page, okay, which I'll show you. So you just draw this, I'll just paste, and then we are going to rotate. We're going to rotate left by 90 degrees, right? So if you look at this case, right, it's the same as this way, right? Compression tensile, you can see that, right? And then the next one you do, you just rotate your page again, and you just rotate another 90 degrees. Okay. So if your moment vector is pointing downwards, okay, tensile is on the left and compression is on the right. So you again use right hand rule, it's the same thing. And then finally, if you have, okay, and as I said, this is by rotating your page. I'm doing this just to show you, okay. And then we rotate to the left again. Okay, if your moment vector is this way, then on the right hand side is all the bottom half is compression tensile. So this will be easier for you to visualize. Okay. Anyway, once we have done all this, okay, we know that mz, okay, mz, we are aware that mz is equal to m cos theta. And we also know that my is equal to m sine theta. Okay. Now, I think you all know how to find second moment of area really, really well. Okay. But more important now is why, right? Why, when we have two axes or we have moment applied about two axes, the structure is known as centric unsymmetrical bending. Okay, so I'm going to copy the whole thing again. So why when the moment is applied on two axes, okay, the structure or axis, not x, two is plural. The structure is known as centric unsymmetrical bending. Okay, why is that? Okay, so we are going to again call 2 points. So alpha, or all the 4 points, beta, right, I, and J. Okay, we're going to do that. So we are going to analyze the stresses, right? We are going to analyze the stresses. So the first one we're going to analyze based on My. Okay, we're going to analyze based on My. So I'll copy this, or I'll copy this. Okay, I'll paste, right? And then we know that, again, to apologize for this. And then this is our z-axis, and this is our y-axis. Okay, and then our try one word. Okay, so we know, I'm going to draw our moment about y. So our moment about y is in this direction, right? This is our moment about y, right? And then if you use right hand rule, this is compression, and this is tensile. Okay, and then on the right hand side, we are going to have moment about z, right? So I will sketch this out. Then we have the green, our centroid along the z-axis, and we also have centroid along the y-axis. Okay, then we are going to have moment about z, and using right hand rule, this is compression, and this is tensile. Okay, then again, our label alpha, beta, alpha, beta, I, J, and again I and J. Okay, so I'm going to now write out. So we have points. So we have alpha, beta, point I, point J. And the first one we are going to work based on stress X is equal to My over Iyy multiplied by Z. Okay. So we're going to focus moment about Y is this. Okay. Right. And then towards the centroid about My is, I'm going to highlight in yellow. Okay, so this is the center, the axis which that My is applying on. Okay, so point anything on the left hand side is going to be tensile. Anything on the right hand side of the vertical axis or about the y axis is in what? Compression. Okay, so alpha is going to be positive tensile, right? Beta is going to be compression, negative. I is going to be tensile, positive. J is going to be compression. Okay. So this is very obvious, right? So next we are going to look at moment caused by, or stresses caused by moment about the z-axis. So the next one is stress X is equal to mz over izz multiplied by y. Okay. So the axis that moment is acting on is applying on the z-axis. Below the z-axis is going to be tensile. Above the z-axis is going to be what? Compression. Okay. So now we just need to write alpha is compression, so minus. Beta is compression, minus. Okay. I is in tension, positive. J is in tension, is positive. So something very interesting occur now. Okay. So if you were to focus on this table, if I have your attention on this table that we're writing out, over here we will have maximum, or point beta is, we're going to have the maximum what? Compression. Okay. And then point I, right? Point I will be equal to your maximum tensile. Right? And why this is non-symmetry? Because most of the time, right, or all the time, where we have stress alpha is not equal to stress what? Beta. Okay, stress X at point alpha will never be equal to stress X at point beta. And stress in the X direction at point I will never be equal to stress X direction at point J will never be equal. Okay, so because of this reason, that is why the structure is centric, unsymmetrical, bending. Okay. In symmetrical bending, stress X alpha will be equal to stress X beta. Stress Xi will be equal to stress Xj. For this case, it will never be. Okay, so that is why this is classified as unsymmetrical, centric, unsymmetrical bending. Okay, so for just to finish up before we do an example, so for centric, unsymmetrical bending, the applied moment is acting, or are acting on two axis. Okay, that's the reason. Okay, enough theory. Let's look at example number 1. Okay, let's look at one example. Okay, I posted the example on I posted this diagram. Okay, so we're going to do a few things. We're going to determine. Okay, we're going to determine the stresses or the normal stresses